Now that we've explored a variety of methods for gathering and presenting our data, we're finally ready to start playing with it. That is, to really look at our data and interpret what it's telling us. The first stage of data analysis is descriptive statistics. These are calculations that help us describe our data. We aren't making inferences yet or checking to see if correlations or patterns exist or anything like that. We're working with a single variable at a time and identifying three main things about it. Its central tendency, or the middle of the variable, the variation within the variable, and the frequency of particular values within the variable. Until now, we've only been able to theorize about these things. Before I give a test, I may have a good guess about how well my students will do. It's not until after I grade the exams and see their results, though, that I have real data to see whether my guess was as good as I thought. When I return a graded exam to my students, I tell them the mean, median, and mode for the class and the number of A's, B's, and C's or below. I'm describing to them, my audience, the collective data from their exam without revealing the raw scores. This is why we do descriptive statistics. I can show you a data set full of numbers, dozens of variables, hundreds of cases. Looking at that raw data, it's not really possible for our human minds to comprehend what it's telling us. We need to describe it somehow in a way that will let us easily understand and report on it. For example, let's say you're interested in terrorism around the world and want to know what the typical number of fatalities is in a terrorist attack. You go to the University of Maryland's Global Terrorism Database. You can pull a list of every attack and see which countries listed, when the attacks occurred, who the target was, and the number of fatalities. Very useful information. But if you try to scroll through the 180,000 attacks they list at the time of this taping, it's going to take you a long time, and you aren't going to be able to process that raw information. Instead, you can download the dataset into your stats program of choice and run a few calculations. You'd find that the global average number of fatalities per incident is 1.74 between 1969 and 2009. See? Much more useful. Descriptive statistics are fairly simple calculations that help us describe our data. There are three broad categories we're going to look at now: central tendency, variation, and frequency. Central tendency is about calculating the middle or center of our data. If you've ever calculated an average or mean or median or a mode, you've calculated central tendency. All these measures can be easily calculated in any spreadsheet or statistics program. Use them. It's tedious to do the calculations by hand or calculator, and we are much more prone to mistakes than computers. First up is the mean. The mean is also called the average. You calculate it by adding up each score, data point, value, whatever you want to call it, and then dividing the sum by the number of scores. In college, we have a grade point average. In each class, you earn a certain number of points based on your grade: 4 for an A, 3 for a B, etc., per credit hour. If you add those up and divide by the number of credit hours, you get your GPA. We use averages like this all the time, and they're a great measure of the middle of your data. But they do have some disadvantages. Averages are very susceptible to outliers, data points that differ significantly from the rest. To illustrate, let's take a set of data. Let's say that we want to determine the average age of a Great Courses subscriber. I take a random sample of 5 people. Not big enough, really, but good for our purposes right now just to understand means. Let's say the ages of those 5 people are 35, 40, 45, 50, and 55. We add those up, we get 225. Divide by 5 total data points, the average is 45. Great. But what if we change just one person's age? What if our 55-year-old was actually 85? Now our sum is 255, 30 higher than before. Divide that by 5 and our average age is 51. Just one data point change increased our average by 6 points. Okay, you might say, but the sample size is small. Good observation. And if there was more data, it wouldn't have such a big impact. Well, maybe. If we had 100 people in our sample and 99 of them were 45 years old and one was 85, what would the average be? 45.4. Less than before, but you can see that our one person is still driving up the average all by him or herself. But let's look at bigger numbers. Imagine we wanted to know the middle income for our community. Again, we randomly sample 5 people. Yes, that's still not enough people, bear with me. Let's say that the incomes of our 5 people are $20,000 a year, $30,000, $40,000, $50,000, and $60,000. Add those up, you get $200,000. Divide by 5, you get an average of $40,000. Now, let's say that the $20,000 person gets their big break in show business and now earns $10 million a year. What's the average now? $2,036,000. Look at the difference just one outlier made. And it works the other way too. Say our showbiz person crashes big time. They've lost their huge salary and their old job earning $20,000. They're crashing with relatives and living on savings, so their salary is now 0. The new average of our sample of 5 people, $36,000. If you look at your data and see some outliers that might be influencing your mean, you have a few options. First, you can trim your mean, eliminate a certain number of scores on one or both ends, and report your mean as a trimmed mean. This keeps those outliers from affecting the mean because you're outright excluding them from your calculations. The second option is to use the median instead. The median is a measure of the middle where 50% of your data is higher and 50% is lower than that number. To calculate it, you take all of your data points, order them from highest to lowest, and then find the one in the middle. And if you have an even number of data points, you just take the average of the 2 in the middle. The median isn't susceptible to outliers like the mean. Because you're ordering your data and identifying the middle value, it doesn't matter how big or small the other numbers are, you only need the one in the middle. The median of our original salaries, the one in increments from 20 to 60,000, is 40,000. That's the same as the mean. When you order the numbers from highest to lowest, 40,000 is the middle point, with 20 and 30,000 below and 50 and 60,000 above. If you change 20,000 to 0, the median doesn't change at all. 0 is still below the middle point, so changing the value has no impact on the median. Now, when our $20,000 earner's salary jumps to $10 million, it does change the median, but only to 50,000, the new middle value. The reason is that a low value number, 20,000, is gone and replaced by a high value number. So the new order is 30,000, 40,000, 50,000, 60,000, and 10 million. That 10 million could become 100 million, and the median would still be 50,000. For this reason, household income is usually reported as median income rather than average income. This prevents very large or very small salaries from overly influencing the data. So anytime you suspect a skew in your data due to some outlying high or low numbers, use the median. Basically, the mean is generally our best measure of the middle so long as the distribution of the data is generally normal and without a small number of very high or low numbers skewing the results. In that case, use the median. And we'll talk more about normal distributions a little later today. Our final measure of the middle is the mode. The mode is simply the most frequently occurring value in our data. That's it. If there's no value that repeats, then there's no mode. To calculate the mode, just count the number of times each value appears in your data. The one that appears most frequently is your mode. The calculations you can do depend very strongly on the kind of data you collected, particularly its level of measurement. If you recall, we generally talk about 4 levels of measurement. The first is nominal, in which we have different but unrankable categories, like with marital status or ethnicity. The second, ordinal, is where we can rank our categories in order, but can't establish distance between them. A 5-point scale of satisfaction from very satisfied to very unsatisfied is at the ordinal level of measurement. At the third level, the interval level, We can establish the exact distance between categories, but there's no true zero that allows for percentages or ratios. So at the interval level, I can say that one person is 3 inches taller than another, but I might not know either person's exact height. The ratio level can provide that exactitude, though. Ratio variables do all the things that nominal, ordinal, and interval variables do, but also add that true zero, so it makes sense to speak in terms of ratios or percentages. Age, salary, weight, these can all be expressed as ratio level variables. Someone who weighs 200 pounds is twice as heavy as someone who weighs 100 pounds. If you make $50,000 a year, you make 50% of someone with a salary of $100,000 a year. 0 pounds does mean absence of weight, and $0 means absence of salary. So what does it mean to calculate a mean if you have a nominal variable? You really can't. There aren't any numbers to add up. Even if you assign numbers to the categories, say single is 1, married 2, divorced 3, and so on, what does a mean of 2.5, well, mean? Nothing. So we can't calculate a mean with nominal or ordinal data. We also can't calculate a median with nominal data. This requires us to put our data in order from highest to lowest, right? Well, if we can't rank our data, we can't order it, so that's out too. Pretty much all we can do with nominal data is report the modal category. We've previously discussed that as a general rule, it's better to gather as precise a set of data as possible. One reason is that you can always collapse variable categories down to something less precise, but you can't do the reverse. If you gather interval or ratio data, you can do all 3 calculations. At the nominal level, you're really restricted with what you can do. Okay, so that's central tendency. Our next set of descriptive statistics focuses on variation, specifically how much variation there is in the data. Are there lots of different values, or do the same values show up a lot? See, knowing the middle is important, but not enough. If I tell you that the mean age of our sample of 5 Great Courses subscribers is 45, that can mean a lot of things. Each of the following sets of data have a mean of 45. Set 1. 45, 45, 45, 45, 45. Set 2, 40, 40, 45, 50, 50. And set 3, 20, 20, 45, 70, 70. But notice the differences in variation in those 3 sets of data. We may want to know whether the mean is 45 because everyone is 45, or if there is a narrow or wide distribution of the data around 45. And if our mode is 45, is this because 45 appeared 2 times and every other data point once, or because every single respondent is 45? Inquiring minds want to know. For variation, we're going to focus on 2 indicators, the range and the standard deviation. The range is the distance between the highest point, or maximum, and the lowest point, or minimum, in the data. You calculate it by subtracting the minimum from the maximum. You can also just report it in terms of the minimum and the maximum. So for the set of 5 45s, the range is 0. The minimum and maximum are both 45. For the second set, the minimum is 40 and the maximum 50, so the range can be expressed as either 40 to 50 or 10. For the third set, the range is 20 to 70 or 50. Temperature ranges are a kind of range that gets reported all the time. Another example of a range would be when you give a time estimate for a long trip, a figure that can vary from day to day and hour to hour depending on traffic, weather, and other factors. The standard deviation is another very useful calculation for descriptive statistics. It tells us the average distance of the scores in our dataset from the mean. So it's a measure of the overall variation in our variable. It doesn't tell us about the specific distance of one score from the mean. We'll talk about z-scores a little later, which will tell us that. But we get a good sense of the overall picture of the data. Now, I could walk you through a standard deviation calculation, but I recommend you let a stats program do the work for you, as there's less risk of error. In our example of 5 45s, the standard deviation is 0. The average distance of our scores from the mean is 0 because each score is the mean. In our second set of subscriber ages, it's 5. In our third set of data, which has the most variation, it's 25. As you can see, the more variability there is in a variable, the higher the standard deviation. We'll come back to standard deviation a little later when we discuss z-scores. First, let's look at our final area of descriptive statistics, frequency. This is where we look at how frequently each value shows up in the data. How many Great Courses subscribers are 45 versus 20 versus 65? Mode tells us which category occurs most often, but we may also want to know which values never show up at all. To calculate frequency, all you have to do is count up how frequently each value appears in the data. Again, spreadsheet and stats programs can and should do this for you. The problem is how to report this data. As we learned earlier, simply reporting the results for every value in the dataset is tedious and not very useful. With central tendency and variation, we turn to single statistics. With frequency, we tend to rely on visual depictions. First, you can create a frequency table. This reports in table form how frequently each value, or more commonly range of values, appears in the data. As a rule of thumb, you don't want to report more than 6 or 7 values, or it becomes too much data to process. So if you have more than 7 or so values in your data set, create value ranges that make sense, and then report the frequency on those. So if I'm reporting on the ages of Great Courses subscribers, and of the now 100 people I surveyed, there are 40 different ages represented, I wouldn't do a table reporting all 40 individually. Instead, I'd create age ranges, under 18, 18 to 25, 26 to 35, etc. The ranges should be meaningful and relatively equal. Don't give in to any temptation to use these tables to manipulate your results into telling the story you want to tell. Another option is to create a frequency distribution in your spreadsheet or stats program. This is a plotted graph. On the vertical or y-axis, you put the frequencies, ranging from the minimum number of times a value is reported, which might be 0, to the maximum, which could be as high as n, the total number of data points. On the horizontal or x-axis, you put the values themselves from low to high, or a range of values if you have more than 7 or so in your data set. Then plot a graph where each point is at the intersection of the value and the number of times it appears in your data set. This is often reported as a bar chart. Most word processing programs have table and chart making features that you can use to make visually appealing tables and charts. These graphics are great visual tools to see how frequently different values show up in the data. What they give us is a distribution, a visual depiction of how many times a particular value shows up in your data. Typically, we visualize a distribution using a curved line that connects our data points. That curved line represents our distribution, and everything under the line between it and the x-axis contains all of our cases. By looking at the shape of the distribution, you can see whether the values in the data tend to cluster around the median or are more widely dispersed. You can see whether there's a skew in the data toward lower or higher numbers, which is useful in telling you whether you should use a mean or a median. If our measures of central tendency, the mean, median, and mode, are equal to each other, then we get a nice symmetrical curve, what we typically call a bell curve. When this happens, our distribution or curve is called normal. A normal distribution tells us certain information about a set of data. We know, for example, that about 68% of our data points are going to fall within 1 standard deviation of the mean. That is, if you take the mean and add the standard deviation to it, this gives you an upper limit. Then subtract the standard deviation from the mean to get a lower limit. The area between the upper limit and the lower limit in a normal distribution will be 68% of your cases. If you add 2 standard deviations above and below the mean, then 95% of your cases will fall between the upper and lower limit. 3 standard deviations, 99%. Now, we aren't going to go into the math here on why that's the case. It's an attribute of the normal distribution, though, and it's something super useful to know as it will help you describe your data. I've said before in this course that you can't just assume something is true of a wider population because it seems to be true in your own personal experience of it. If you live in a community of super tall people, you might think that being over 6 feet is average or normal. Your entire experience might be of super tall people, so it's easy to make that assumption. But if you look at the entire population, not just of your community, but of humans in your entire country or the world, you'd see that actually your community is not normal. That is, the average of height in your community is not near the mean. The average height of a woman in the United States is about 5 foot 3 inches. Let's pretend that we randomly sampled from the US 1,000 people and measured their heights. One person from your town, let's call it super tall town, is in the sample, a woman who is 6 foot 2. The mean of the data is 5 foot 3 with a standard deviation, let's say, of 4 inches. Again, for the sake of this exercise, assume our distribution is normal. Height usually is. What this means is that about 68%, or 680 out of 1,000 women, are between 4 foot 11 inches and 5 foot 7 inches. We took that mean of 5 foot 3 and added and subtracted one standard deviation of 4 inches to get those upper and lower limits. It also means that 95% of the women, 950 of them, are between 4 foot 7 inches and 5 foot 11. That's 2 standard deviations from the mean. Our super tall town person is 6 foot 2. That's within 3 standard deviations, or 99%. That would still leave 10 women who are extreme outliers, shorter than 4 foot 3 or taller than 6 foot 3. Do you see how making assumptions about the population based on a non-representative sample can lead to poor conclusions? Sometimes we use a standardized normal distribution, which is a theoretical distribution where the mean is 0, the standard deviation is 1, and the number of cases is infinite. Through the magic of calculus, the standardized normal distribution can tell us something about z-scores. Calculations that, among other things, allow us to describe our data on multiple variables, even if they're expressed in different units. What do I mean by that? Well, let's say that you have a bunch of data on different features of breakfast restaurants. You rated them on their decor, customer service, food, drinks, accessibility, menu variety, cleanliness. You get the idea. This might be because you take breakfast very seriously or because you work in a quality control field. You've rated 50 different breakfast establishments on these criteria using a variety of scales and questions. Now you want to know how one case stacks up relative to the others. One way to do this is to calculate the z-score. A z-score expresses the distance of a single case from the mean of the variable, and it does so in units of the standard deviation. If I tell you that Pancakes R Us is 4 points from the mean on the variable of cleanliness, that doesn't tell you very much information. Is 4 points a lot or a little? We'd need a lot more information to be able to evaluate that. But if I tell you that Pancakes R Us is 4 standard deviations from the mean, that alone tells you quite a bit about that place relative to the others. In a normal distribution, remember, 99% of cases will be within 3 standard deviations from the mean. Pancakes R Us is either the cleanest restaurant imaginable or dirty beyond belief. Z-scores then express your data in units of the standard deviation. So a z-score of 1.5 means that on that variable, the case is 1.5 standard deviations above the mean. A z-score of negative 0.6 means the case is 0.6 standard deviations below the mean. Now, the formula to calculate a z-score is very simple. All you need is your score or value on the variable for this data point, the mean for the variable, and the standard deviation. The formula to find the individual z-score is the score minus the mean divided by the standard deviation. Remember our data on super tall town and our friend who was 6 foot 2? We said in that case that the mean was 5'3" with a standard deviation of 4 inches. So we can calculate the z-score for this case. The score is 74 inches, 6'2". The mean is 63 inches. If you subtract 63 from 74, you get 11 inches. Divide that by 4, the standard deviation, you get 2.75. Our friend, let's call her Justine, is 2.7 standard deviations above the mean. As we said earlier, she's just within 3 standard deviations of the mean. Note that a z-score can be negative. If we take another friend from Everytown, US, let's call her Amy. She might be shorter than the mean. Let's say that Amy is 5 feet tall or 60 inches. The mean and standard deviation stay the same. Amy is just another case. Now we subtract 63 from 60, we get -3. Divide that by 4, we get -0.75. Amy is 0.75 standard deviations below the mean. Calculating z-scores can be very useful. Using units of standard deviation makes it easy to assess how a case fits into the overall distribution. Just knowing that a case is 2.75 standard deviations above the mean or 0.75 deviations below it tells us some interesting information about that case. If the z-score is 0, that tells us that its value is the same as the mean, meaning that on that variable, it's an average case. If you're doing case study research and want to select either a typical or deviant case to study, calculating z-scores can tell you whether or not a case is typical, close to 0 in the mean, or deviant, 3 or higher. We can also use z-values to tell us something about the variable more broadly. If we know a particular z-score and use the standardized normal distribution, we can find out how many cases fall between the mean and that score. If you want to do this, grab a normal curve table. These take different forms, but typically they have 2 columns of information: z-scores and areas between that score and the mean. That second column will tell you what percentage of cases falls between the mean and that particular z-score. Remember how we said that in a normal curve, 68% of cases fall within 1 standard deviation of the mean. That means that half of that, 34% of cases, will be between the mean and a z-score of 1, and 34% between the mean and a z-score of -1. If you look at a normal curve table and look for a z-score of 1, you will see 0.3414. Double that to get the range of 1 standard deviation above and below the mean, and voila, 0.68 or 68%. You can do this for any z-score. Returning to Pancakes R Us and its z-score of 4, you would see that the area between the mean and this z-score is 0.4999. If you double that, you get 0.9998. That means fewer than 0.01% of cases will be further away from the mean than Pancakes R Us. Another use of z-scores is to look across variables. If you have variables in different units, they can be hard to compare. By putting all of your variables into units of z-scores, you've standardized the scores into something easily compared across variables. So if we return to our breakfast example, let's say we have a cleanliness score on a scale of 1 to 10, an accessibility score on a scale of 1 to 5, and a customer service scale of 0 to 100. Usually you can avoid this kind of problem with careful survey design, but sometimes you can't control the data you have. Let's say that Pancakes R Us has scores as follows. 1 out of 10 on cleanliness. The mean is 5 and the standard deviation is 4. 1 out of 5 on accessibility, the mean is 3, the standard deviation is 1, and 65 out of 100 on customer service, with a mean of 75 and a standard deviation of 6. Imagine we looked at a similar set of scores for the other 49 restaurants. Where does Pancakes R Us rank amongst them? Is it an average case, a low-ranking one, or a high-ranking one? Looking at the data in this raw form, it's hard to say, but if we standardize our data into z-scores, we can actually get a decent sense of the case. For Pancakes R Us, its z-scores are as follows. For cleanliness, its z-score is -1. A score of 1 minus a mean of 5 is -4, and divided by the standard deviation of 4 is -1. For accessibility, its z-score is -2. A score of 1 minus the mean of 3 is -2, divided by the standard deviation 1 is -2. And for customer service, its z-score is -1.67. The score of 65 minus a mean of 75 is -10, and divided by the standard deviation 6 is -1.67. Now, we can more easily see that Pancakes R Us is consistently below the mean by one or more standard deviations. The average z-score is -1.56, so on average, Pancakes R Us is 1.56 standard deviations below the mean. This tells us with one simple number that we probably shouldn't book a reservation anytime soon. That is the benefit of descriptive statistics. We take our raw data and transform it through some basic calculations into a form that is more easily understood, both by us as analysts and by our readers. Calculations of central tendency, variation, and frequency, particularly when combined with thoughts about the normal curve and z-scores, can be very helpful tools in understanding the data we have before us. Next time, we'll learn how to make inferences from our data and really start seeing if the relationships and patterns we expect are supported by the data.